So I'm very happy to introduce today Dusa McDuff from Colombia. And she will talk about embedding ellipsoids in the one-point blow-up of CP2.
Okay, so it's a very great pleasure to talk to you all. I'm reporting on a project that we did with this WisCon group, Women in Symplectic Geometry and Contact Topology, I think, sponsored. They're a group sponsored by the AWM that's trying to organize women, sort of vertically integrated bunches of women together to work together. So our group ranges from graduate students through postdocs through senior people, right? And we actually had a good time working on this. I wouldn't have done it if it hadn't been for this project. But it turned out that just about at the time of our original deadline, which was sometime in March, we were just started to discover interesting things. And then we went into lockdown, and I've spent many happy hours in lockdown working on this problem and finding, with my collaborators and finding more interesting things. So I'm reporting on it. Now, this is a very special problem, which is very technical. And so it's rather specialized. On the other hand, I think it's fun. So here we go. So let me just remind you what we're talking about. We're talking about embeddings of the open ellipsoid E1Z, which has got a factor 1, the one axis of size 1 and one axis of area Z, into a scaling of a symplectic 4 manifold. And then you want to know, if you fix Z, what's the smallest scaling you can embed your ellipsoid into. And it turns out, so that's CZX, this infimum. And it turns out, well, it's suddenly, there's a volume lower bound because these embeddings preserve volume, and therefore you have a quadratic lower bound, which here I'm writing as CXZ is bigger than or equal to the square root of Z over the volume of X omega. And here I'm assuming the volume of X omega has been properly normalized to make that correct. But anyway, there's some volume bound like that. And then you know that when Z is, the ellipsoid is sufficiently long and skinny and X is a sufficiently reasonable domain, then the volume is the only constraint, so that these functions agree for large Z. And the other easy fact is that there's a scaling estimate that Cx of lambda Z is less than or equal to lambda times Cx of Z, and that's simply because E1 lambda Z embeds in lambda times E1Z. So there's that. And the problem is just to compute this function. And we're looking at the case when the target is the blow up of a ball or the blow up of CP1, CP2 rather. And the B refers to the fact that we assume the line has got size 1 and we assume the exceptional divisor got size B. So B is going to be, yes, the interesting case is B is not very some positive number in between 0 and 1.
About
question? No, something else. Okay, so when B is 0, that's, you haven't blown up at all. And then you have a perfectly nice function, which you either think of as embeddings into the ball, or it's the same thing, embeddings into CP2. And this function was, Felix and I worked it out, and it had this graph, which you're probably all familiar with, but I just thought I should tell you. I don't know if I could, yeah, I can point a little bit. So there are 3 regions of this graph. When Z is sufficiently large here, Z is bigger than up in this bit of it, it's just a volume constraint. So here it's just volume. The transitional region in between 2 to the 4th and 17/6, where it's got some, it's not necessarily equal to the volume. And then when Z is less than 2 to the 4th, you get this infinite staircase, where it means it goes up, starts at 1, and it goes up here, it goes up to 2 along this line through the origin, then it goes horizontally, and this is on the volume curve. This is a bad figure, I'm sorry to say, because I drew it. And then it goes along this line, again through the origin, up to 5, 2.5, then it goes along straight till it hits the volume, and then it goes up and along and up and along, and the numerics are just governed by the Fibonacci numbers. And so there are reasons why you have these outer corners. There are obstructions here. And at the inner corners, these inner corners lie on the volume curve, and therefore there are full fillings at the inner corners. And once you know this is what the structure is, then you don't need to do all the work that Felix and I did. You can just prove that there are obstructions here, so you have to have it as big as it is there. And then you can prove that you have full fillings here, which are very nice geometric methods now using almost toric fibrations and things. And then the graph has to look like this because of the scaling property, and also the obvious thing that this function is never decreases. So if it's up, if it's a level, it has its same value there and there, it's got to be constant on its interval. So, now there are very nice proofs, and actually there's, you may think this is a sort of very numerical and boring problem, but the numerics of these almost toric fibrations, that structure comes up in many other situations. For example, when you're trying to find monotone Lagrangian submanifolds of various toric manifolds and things. So I think the numerics are interesting, and they're not just confined to this problem. And then, so I've said that, and so that's all I was going to say about that. So now, let's look at other targets. So there are many, many questions about, papers trying to explain what this function looks like when you have a different x. And there was a whole day called Ellipsoid Day devoted to that in June. So I'm really not going to say anything about that. And if you're interested, you can go back. I mean, people were talking about this very nicely. But anyway, what are our main references? Well, of course, there's a paper I wrote with Felix about the ball, because that's what I know, right? And then there was a paper by Usher, where he looked at a similar kind of problem, because he was looking into a polydisk, which is a 2-disk times a 2-disk, but his B here was irrational. And he was looking to see what he could find here for various irrational Bs. And he found a doubly infinite family of staircases, each with a different irrational value of B, and they were related by certain numerical moves, some of them purely numerical. And then he found these really fascinating things. These are what called Brahma-Gupta moves, which date back to the sort of old Arabic geometers in the 7th century that they're related to the properties of Diophantine equations. So there was some transformation in Diophantine equations that gave you some new solutions. And, that's incredibly impressive to sort of have mathematics going back that time. And so it gave us inspiration and also a very useful estimate. So we used a little of his methods, not all of them. And then the other paper, the other influential papers by Dan Cristofaro Gardner, Tara Mandini, and Anarita Pires, which is about staircases and rational toric manifolds. And actually, okay. And it contains this theorem, which is essential for us. So if we have we're just restricting to HB, so this blow up, if it has a staircase, then in this paper they show that the steps of the staircase, a staircase sort of goes up in steps, and the steps of the staircase have to accumulate at one particular point, which is called the accumulation point, which is a unique solution of this quadratic equation, which is a unique solution which is bigger than 1, because the product of the roots is 1. So there's one solution bigger than 1. So there's what the accumulation point has to be. And so when B is 0, this accumulation point is 2 to the 4th. And what they did was adapt our argument that sort of was dealing with that kind of thing to this very beautiful general statement. And then the thing is that if at the accumulation point, we'd say the accumulation point is unobstructed in the sense that the value of the capacity function is the volume. So whatever it is elsewhere, it's got to be the volume there. And in the toric model, this equation, of course, doesn't come out of nowhere. In the toric model, then 3 minus b is the affine length of the boundary, if you scale things correctly, and 1 minus b squared is twice the area. So it's some very natural scale invariant measure of a polytope, and this applies to the kind of convex polytopes they were looking at. They were looking at rational convex polytopes. So this very general theorem. So we really started from here. Usher didn't know that. So if Usher had known that, he might have phrased his results differently, but this is a new result that he didn't know. Okay, so what is this curve? So it's a function z goes to ac z. Z goes to ac b, where it's this quadratic. And it's not a one-to-one function. It's not injective. while in the case, say, of the polydisk, it is injective. So that means that it really has a different structure here. And what it does is, as B, it takes its minimum at a third. And when B is from 0 to 1/3, it decreases from 2 to the 4th, which is the accumulation point for the ball, to this value here, which is it. At 1/3, there is another staircase, which was discovered by Anna Rita and those 4 groups of people. And there is another staircase at 1/3, and this is its accumulation point, which is this third. And then this is the minimum of this function, and then it increases. And here's a graph of it. So here's the graph. Now, this is a rather cunning picture because you're thinking of a parameterized curve where this coordinate here is a z coordinate, and the vertical coordinate is the volume. And what you're seeing is, here's when B is 0. So you start here at 2 to the 4th, and whatever the appropriate volume is, which is 2 squared. And then you go down to 6, which is taken at 1/6. This point is taken when B is 1/5. And it's a minimum of the volume. And then you go to when B is 1/3, this green point here is the accumulation point for this staircase in H1/3. And then the function increases there. So it sort of goes back on itself. And so it means that there are 2 different regimes in our problem. There's a regime when B is bigger than 1/3, and a regime when B is less than 1/3. And of course, 1/6 is an important point because that's a minimum. Okay, so that's a sort of important function. And so what did we find? We did eventually, it took us a long time, but we did eventually find new staircases. For a long time, we couldn't see anything. And then we found 3 new double families of staircases. So, you'll see what they're labeled in a second. And if they're labeled with a little l at the bottom, they're ascending staircases. They go up, and the ones labeled U go down. And here are our families. So this is our family, which I call the U family, the upper family. And for the upper family, for each value of n, there's an ascending and a descending staircase. And the values of B are bigger than 1/3. They're sort of large values of B. And their accumulation points live in 7 infinity, in between 7 and infinity. And this set of values here, these bn's go to infinity. So that's our first family. A second family I call lower, sorry. And the lower family is, all these staircases, it turned out we discovered, are extensions of the Fibonacci staircase. So this family, if you allow n to be 0 in SL0, this is the Fibonacci staircase at B equals 0. And then we have these other families when n is bigger than 0, we have a pair, an ascending and a descending, and they have values of B in between 0 and 1/5, and Bn is going to 1/5. And then we have another family, which is actually the first family we discovered, which lives in a range. This is B is in between 1/5, and this is less than 1/3. So it's in between 1/5 and 1/3. There's, again, pairs of staircases, and the bn's converge to 1/5. So if you go back to our diagram here, the U staircases, live in here, up here. The L staircases live here, and the E staircases live there. And the L staircases and E staircases converge, the sort of accumulation points converge to 1/6. And we do show, another thing we show is that at 1/6 there is no staircase. I may have told you that at 6. I may tell you that later. Anyway, so that's our 3 families of staircases. And then we find these staircases, and they're related by symmetries, which I will try and explain later. They're what we can see of the Brahmagupta moves. And so the symmetries are acting very nicely on the z coordinates. So they act by these fractional linear transformations, like this one. Psi is a reflection, so its order is square 2. It fixes the point 7, and it actually takes the U staircases to the L staircases. So that's a symmetry operation. And of course, there are infinitely many symmetries, but we've only worked out, we've only actually proved the existence of these 3 staircases. We've got many other conjectured staircases. So these staircases are what called two-periodic. So it means that their steps have z coordinates of the form like this. So these are the steps actually of this SU, this decreasing staircase. So we put them in continued fraction form, which I will explain. And they're two periodic because the continued fraction has got this pair, repeating pair. And then this is what we call the end. And actually there are two choices of end, but I've just given you one of them. And what one conjecture is that all the two periodic staircases are images of a staircase of this form under some symmetry operation. That's one conjecture we have. No idea how to prove it, but there you are, there's an idea. We found other staircases because we sort of work partly by computer and partly by, you know, sort of proving things. And by computer, we found plenty of other potential staircases that are 4-periodic, 6-periodic, and so on. But we haven't started proving that they actually satisfy the right conditions. So, you know, they're there, but I'm not going to say anything about them. We will publish a second paper where we will perhaps talk about them. Anyway, so that's one feature, these 3 staircases that we found. The other feature we discovered is these blocked B intervals. So there are 3 families of staircases, U, L, and E. And for each family, there is a set of B values. We've got these 2 staircases, an increasing one for this value of B and a decreasing one with that value of B. And the claim is that in between those 2 values, there are no staircases. Those are blocked B intervals. So the claim is that for each, you know, star, these U, L, or E, the set of B values between these things is obstructed. So that means that the capacity function is definitely bigger than the volume on those intervals. And here is a picture which draws a little bit of, we're looking at the upper family. So this is the J, what I call JU0. So it's the interval that's blocked by the bottom one of those U classes. And so our first staircase, the descending staircase, exists on this value of B, and there's an ascending staircase which lives on that value of B. And then we have a little green interval which we don't know, that contains 4-periodic, 6-periodic, 8-periodic, many, many staircases, but we haven't figured that out. Then we have another interval, which is this red interval, which comes from our obstruction. There's an obstruction which I'm going to talk about, which gives you this interval. It's somehow centered at 8. And then so that these are all obstructed, and then we've got an increasing staircase converging at this value and a decreasing staircase converging at that value. And then similarly, I mean, those are, so you see, and these intervals, their lengths, they can, JUN contains a point 2n plus 6, and its length converges to 2. And so we have these very, they're sort of centered 2 apart. So almost all, you see these, and you can hardly see that green interval. I don't know if you can see it, but you know, there's most of the B values are blocked, but there are these other places. Okay. So the general picture, we define block to be the set of B values which are blocked, which are where the capacity function at this special accumulation point is definitely bigger than the volume function, and therefore there could be no staircase, because if there were a staircase, these things would have to be equal. And then we define stair to be the set where you have a staircase. And then we know that stair sits inside the complement of block we call unobstructed. So those are the ones where we have equality here. And we actually know that stair is not equal to unobstructed because we've got 1/5, which is unobstructed, but there's no staircase. And otherwise, I mean, there's probably quite a lot of difference between these sets, but we haven't, you know, there are many questions we haven't looked at. So there's a conjecture which is due to the people writing about these general toric manifolds, Dan, Christopher Gardner, Holm, and the others, that the only rational points in stair are this 0 and 1/3. So there are no other rational points in stair. And all we've proved is that 1/5 is not in stair. But the argument for that is quite complicated, and one would need a better argument to prove this in general. Then the claim is that the irrational points in stair are precisely the endpoints of the components of the open set block. So in other words, the claim is that every staircase that we can find, if it has an irrational accumulation point will be given by sort of an endpoint of a blocking class. Well, we haven't proven that at all, but that's our conjecture. And then, you know, what can we say about the structure of block? Well, we can look at block plus, and I put a Z there to say that this is, you see here, these are intervals of Bs. But the block plus Z is the image under, you take the block B intervals and look at it in, say, from 1/3 to 1. So look at it in the upper interval and then look at the Z. So this, look at the corresponding set of Z. So that's some collection of intervals in this range. And then block minus Z is the same thing, except that we want B's to be less than 1/3. And that's another set of intervals. And then the claim is that these sets, these are Z sets, that they're invariant under certain fractional linear transformations, like this one, phi, which is a reflection. It fixes 6 and it takes infinity to 35/6. It's a reflection fixing 6. And then there's a shift which takes the interval, say, from 36/6 to infinity. It moves it down one, so it goes to an interval to 204/35 to 35/6. So I will say a little bit more about that at the end, but these are our analogues of the Brahmagupta moves, and you can see them very clearly on the Z coordinates. Okay, so that's a conjecture, but you know, some of this is proven. And then there are similar, it's slightly complicated, the relation between block plus and block minus, so I don't want to go into it, but there's a similar statement for block minus, and then also there's a symmetry that takes block plus, everything in block plus should be mirrored by something in block minus, within reason, put it that way. Okay, so that's a general picture that we have for these two periodic well, actually these are for all staircases, they're not two periodic or not. So actually this is a good place to stop, because I'm now going to talk about the proof a little bit. So does anybody have a question at this point? There's no, okay, so that's the general picture. And so what I'm going to do, the plan is to describe for you the ingredients of the proof a little bit, and then to tell you a bit more about how those ingredients spell out in proving some of these statements. Okay, but this is the picture we have. So the technical points in the proof, well, I'm reminding you about how we deal with this problem, that first of all, if you're trying to embed, if you want to know whether, you know, and if you have a ball embedding in a four manifold, then that corresponds to blowing up the manifold, and you get it. If you have a symplectic embedding, you have a symplectic form on the blowup, which is your original form minus it's got size W on the new exceptional divisor. And then the second basic fact is that every rational number has what's called a weight decomposition, which I will say more about. These are the decomposition into some set of rational numbers, where it starts off with 1 and it ends over 1/q, such that you can embed an ellipsoid into your manifold if and only if you can embed this disjoint union of balls into the manifold. And then you put these together and then say, well, you can embed an ellipsoid in a manifold if and only if you can have a symplectic form on an n-fold blowup of HB in a particular class, where you've got the class here. This is the class of the form on HB, right? So it takes, but it's lambda HB. So it takes lambda on the line, lambda B on the first divisor, which is always a special one because that corresponds to the blow up at the target. And then you've got these WI, EI, which correspond to the weight expansion of what the ellipsoid you're embedding. So that gives you something to begin with. And then, you know, then you want to know that there's a symplectic form on this blow up. Well, that means what's the symplectic cone? And that was worked out by Lee and Lee, that there is a form there if and only if, in class alpha, if and only if the volume constraint holds, so alpha squared is positive. And then the other thing is that alpha integrates positively on all the exceptional spheres. And so that means that the instructions are given by exceptional spheres. And, you know, what is an exceptional sphere? Well, it's a special kind of class, which I'm going to write as D little m and then a bold script m, where D is the size of L, m is the weight of the first divisor, and these mi's are the weight of the other divisor. So these are all integers, of course, so that the Diophantine conditions hold. So C1 is 1, and the inner E dot E is -1. So those are the algebraic conditions, the Diophantine conditions. And then you also need to know that this class transforms correctly under Cremona moves, which is a certain geometric transformation of blow up to CP. And that's a geometric condition, which is not so easy to check. Okay, so that's the basics. So we're looking for, we're trying to find relevant exceptional classes which will give us obstructions, basically. And then the condition, so the condition is that you have this embedding if and only if these conditions hold on the weights, and therefore that tells you that the embedding capacity function is bigger than or equal to this number here, which is this size. This thing is meant to be positive, and therefore it means that whatever this is, this sum here, has got to be less than lambda d minus lambda mb, and therefore lambda is bigger than or equal to this inequality. And this number is what we call the, it's a sort of contribution, it's an obstruction coming from the class E, but you notice here that it depends on B. So it depends on the size of your blow up. So that is very different from what happens if you have a sort of fixed target. We're thinking our target is varying. It's got this one parameter family of targets. So the B, of course, is crucial here. And the other thing I didn't, the obstruction, this capacity function is the supremum of all these things. And so you can prove that it actually at any point it equals one of these things, or the volume, one or the other. So it's always given by, it's always equal to an obstruction function here, or it's equal to the volume. Now the good classes, just as in the case that Felix and I looked at, the good classes we call perfect, and actually Usher had these definitions too, that what you want is that this M here is a weight expansion for some number P over Q, because if that's true, then this vector here, M, is parallel to the weight expansion at this point A, which is P over Q, the center thing. So you get the largest thing you can get from that sum. So that gives you the best obstruction. So those are the important classes. And then you get, the form of the obstruction near that point is very nice. It's constant, actually, if A is bigger than, if Z is bigger than A, and it's aligned through the origin if Z is less than A and in some range. So, that, and if E is perfect, the proposition is, and B happens to be M over D, which of course it never is in cases you're interested in, but if it happens to be, then this class is what we call live. In other words, it gives you the capacity function at that point for that value of B. And then the way this is the only way I really know of calculating this function, though there are other ways using ECH, but we have to find some appropriate obstructions, and therefore we have to show that we're dealing with these exceptional classes which are numerically defined but also satisfy satisfy the Cremona condition. Okay, so these are the obstructions I'm using. As I say, there is another way using ECH. So now let me say a little bit more about continued fractions and weight expansion. So this is just review, so some people know it, some people won't. So this is our definition of what we mean by an exceptional divisor, that it means that this tuple here, which describes the weights of all these extra divisors corresponding to the ellipsoid, we want those to come from the weight expansion of P over Q. And how you get the weight expansion of a fraction, you think of this fraction and you write down a square. So here I've illustrated 25 over 9. So 9 is the height, that's Q, and 25 is this length. And what you do is you take this rectangle of height 9 and length 25, and you chop off squares, as many as you can. So we can get 2 squares of size 9, leaving us 7. And then you chop off the 7, and that leaves us a 2 there. And then you chop off as many 2s. You can get 3 2s in, and then you get 2 1s in. And that tells you the weight expansion. It's the size of these blocks. It's 9 9 7 2 2 2 1 1. And to relate that to the continued fractions, the continued fraction you write like this, 2, 1, 3, 2, and that means 2 plus 1 over 1 plus 1 over 3 plus 1 over 2. It's this continued fraction here. And the point is that the numbers you put in here are the multiplicities of the weight. So you've got 2 9s, so that gives you a 2, 1 7, 3 2s, and 2 1s. And then you can check that this number really does represent 25 over 9, and this is a completely general fact. Okay, so that's, you know, this looks neither here nor there, but it turns out to be very important. So now, why do we get the Fibonacci staircase? Well, that's because Fibonacci numbers have really nice continued fractions. And so here I've drawn a picture. Here are the Fibonacci numbers. And what I've done, the ratios, and what I've illustrated is an expression for 8 over 5 here. So 8 over 5, here's 5, and here's 8. And you notice that at each time, you can only chop off 1 until here, because it's only an approximation, you get 2. So our continued fraction is 1, 1, 1, 2. But it's, you know, if you took any other one, you know, 233 over whatever it is, you'd get exactly lots of 1s and then a 2 at the end. And in fact, that's a completely general fact, that if you look at a ratio of Fibonacci numbers, you get lots of 1s and a 2. And if you take the limit of these, which of course is the golden ratio, then you don't see the 2 anymore. You just get lots of 1s. And that's just because of the property of the golden ratio, right? You divide, you take a rectangle, you chop off size 1, and then you get something with exactly the same proportion. So you keep chopping off size 1 and it never ends. So that's, you know, the Fibonacci series have the most beautifully symmetric ratio you could have. And then, you know, if you have ratios, well, our Fibonacci series, our numerics are actually governed not by ratio of adjacent Fibonacci numbers, but ones which are 4 apart. And if ones that are 4 apart have lots of repeated 5 1s. They don't have repeated 1 1s, but they have repeated 5 1s. And this one ends with a 4, because I've got a 5 and a 3. And if I had a 7 and a 3, a 5 and a 1, and if I'd had the other pair, 7 and 3, I would have got a different end there. But this is sort of half the centers and of the Fibonacci stairs. And just as a fact, the continued fraction of a number x is eventually periodic, exactly if x is a quadratic irrational. So that's just, you know, all the numbers we're coming up with, all our accumulation points are quadratic irrationals, and that's because of this fact. Okay. So now armed with this knowledge, let's just look at the Fibonacci stairs again. So the Fibonacci stairs, the steps of the stairs, are given by these perfect classes, where the centers of these classes are ratios of Fibonacci numbers which are difference 4 apart. And of course we have a 0 there because that's the coefficient of the extra blown up divisor that doesn't exist in this case because we're going into the ball. And then the degree is actually the middle Fibonacci number. And so to give you what these look like, the weight expansion for, if you have 5 and 1 here with a 4 here, and has 6 1 and lots of 5 1s and then a 4. If you have a 7 over 3, you get the same thing, lots of 5 1s and a 5 2. So you have these 2 possible endings. You have these, if you like, you have 2 staircases which are intertwining. I mean, this, or you can think of the whole thing as a staircase, but we think of it as a double staircase because it's sort of got 2 strands which intertwine. And I just gave you some examples, like 233 over 34, you can just work it out. Yeah, so I'm just saying that this is a nice staircase because these inner corners lie on the volume constraint. It's very uncluttered. You have these beautiful obstructions. You know, you couldn't really have a nicer staircase. Now, I think the next slide is a picture of what our staircase can look like. Oh, well, no, not quite yet. It will be. So when we blow up a point, then our exceptional classes have D, and then we have this extra factor M, and our blocking classes are called center blocking. If you look at the center, the center of a class like this is terribly important. So you look at the corresponding B. So you look at the B value that gives you, which has accumulation point there. And then you have to choose the right branch of V. And then an exceptional class is called center blocking if this obstruction from this class is blocking, so it's bigger than the volume at the center point. And in that case, there certainly can't be a staircase for the center point because it's blocked. And it can't be, then there's an interval where there can't be a center point. And so we have an interval JB, and there's a corresponding blocked Z interval, which I call IB, which is a set of corresponding accumulation points. In all cases we've investigated, whenever we have a blocking class, we found staircases at the endpoints of IB. And so here, the example, the staircases SU here, will lie at the endpoints of these blocking classes, where they're very, very simple blocking classes because they're centers of these integers. Everything is beautifully integral. So that's one thing you can say, that we have this relation. That's one of the new things that we can say about the relation with the blocking classes and the staircases. And the other thing we can say is this other little point, that our staircases don't always look as nice as the Fibonacci staircases, and they can be almost overshadowed. We've not found any potential staircases that are actually overshadowed, but they can be almost overshadowed in the sense that there's a large obstruction that prevents the steps. If you look at the capacity function never reaches the volume curve. And here is a picture to show you what I mean. So I want to explain what this is. This is our first staircase that we found, SEU0. It's a descending staircase. Here's its accumulation point. It's built on this 5,1 again. And the accumulation point is 5.86 roughly. The B is less than a third. And then we have this glorious picture, which is, let me explain what its ingredients are. So the orange line here, it's a line, but it's a volume constraint, but it's a square root function, but it almost, in this scale, it looks pretty linear. The green line is a parameterized accumulation point curve. So it's B goes to AC B, VB. And what it does, it just marks for you where, when it crosses the volume curve, that's going to be the sort of crucial, it crosses it when B at the value B is equal to B infinity, and also A is equal to the accumulation point of your staircase. So that green line in all the pictures sort of illustrates where your staircase is ending. Then the dark blue line, so that is this and then this. That dark blue line is what you can calculate using ECH capacities easily, a sort of approximation to the capacity function by taking the supremum of all the capacities, all the obstructions of degree less than or equal to 200. And if you're looking at ECH capacities, it's less than or equal to 25,000. So that you can calculate fairly easily, and you see it's this line. And this class here is a straight line coming from the blocking class B0E, which is because we've got a decreasing staircases. That's at the upper end of a blocking class here. And then up here, what it is, it's this degree 3 constraint, which is a very big constraint, but you see it's almost overshadows the staircase, but not quite, because you can see these little things poking out, right? These little things poking out are very high degree obstructions. And what they are, they're graphs of obstruction curves for 3 very large classes E, which I'm not going to try and tell you what they are. But you notice, well, the first one, this big one that you could really see coming out there, is very simple because its numerics are fairly simple in this range. But when you look at the red one, what's plotted here, what's called the ECH capacity. So the numbering is different. So the ECH capacities agree with the, well, actually, I take that back. So we're talking, nothing to do with the, we're talking about the obstruction function from these classes. But the point is that it's only near, you see, here's the break point of the brown class, and it looks beautiful. It goes up on a line and then goes along on a line. If you look at the red class, it's going up on this line and along on a line, but then it goes haywire because you're too far away from the accumulation point. So we have these 3 blocking, these 3 blocking classes, which are part of our staircase. And they do just peak out above this obstruction. But you see that the numerics, actually to prove that this thing happens, is slightly delicate because you can't see it in an easy way. Anyway, that's a picture of what our staircases look like. I think it's a very illuminating picture. Now, our staircases have a special form, and they're what I call pre-staircases. So suppose we just have a sequence, and I'm saying they're perfect. They could actually just satisfy the they could be quasi-perfect, in fact, just satisfy the Diophantine equation. But for simplicity, let's suppose they're perfect. So that means that they've got these centers, right? So the you know, all the things that are governing the M, that large thing is governed by the weight expansion of the center, and then you have these two extra, the degree and then the coordinate on the blow-up point. So what properties has it got to have? Well, it's got to be recursive. So we've got these four numbers, x, dk, mk, pk, and qk. They're integer sequences, and they're meant to all satisfy the same recursion, which for various reasons, you know, sigma is such that sigma plus 4 is a perfect square, and sigma plus 2 is what happens in the recursion. And then the new thing here, the D and P and Q are related by a homogeneous linear equation. Now, in the Fibonacci staircase, of course they are, because that's just, there isn't any M. M is 0, and then this is just that saying C1 is 1. This equation, it turns out to be homogeneous if you look at it in DPQ. But when n can be non-zero, this is a new thing, that you have this homogeneous linear equation. And so that's a new feature that makes it into a pre-staircase. I mean, you have this recursion, which is sort of clear you need something like that. We have this relation. And then the idea is that if all we know are the steps, you know, P over Q, so we know the centers of the steps of our thing, then we define D by the relation. So we know what we know what our relation is of the staircase. And then we define M from the first Diophantine relation, from saying C1 is 1. So that means that the staircase is completely described. If you know the relation, it's completely described by the set of centers, P and Q. And so here's an example. Here's our staircase SU. It's with upper, so it's a decreasing staircase corresponding to the block BU. It's got this limit point, which, as I told you, is 2 periodic, and it's not 5 and 1. It depends on n now. It's 2n plus 5, 2n plus 1. The centers are going to be essentially this, except that instead they chop off, right? You have a k repetition, and then you have some ending, which is 2n plus 4 or 2n, this other ending. The recursion is given by taking sigma to be 2n plus 1 times 2n plus 4. So that's very interesting. That's times, it's a product of these two repeated factors. And then the relation is of this form. And do I say, no, I don't say it here. This is a double staircase because there are two ends, just like the Fibonacci staircase has this property, and they all have the same recursion. All our staircases have the same recursion. Once you fixed n, we have a parameter. Actually, Usher also had a parameter n that sort of fixed its recursion. And then, but the relation is different for each of our different staircase families. But you notice this relation here, well, it sort of depends on n, but the coefficients are nice linear functions of n. So it's sort of one linear relation, linear in n, for each kind of staircase. And, you know, when is a pre-staircase an actual staircase? So a pre-staircase is just this family of, say, perfect classes. And because of the recursion, it's very easy to prove that the ratios, the steps, converge to some number, and that the M over D converges to some number. And it's actually, because each class is obstructed, because these are perfect classes, and so they actually are above the volume class, it's very easy to prove that the accumulation point, you know, these A's and B's have to satisfy the equation. So even if these were not perfect classes and they weren't actually live, so they weren't really giving you the obstruction function, well, as long as you have a pre-staircase consisting of a sequence of classes with these numerical properties, you know the argument in that Torek paper applies to show that you know that you have this relation. And then if the EK are perfect, then we know that these classes are live at the center points. And therefore, because of so that means that CHB at BK is given at PK over QK by this value, which of course is very small. It's very close to the volume. And therefore, just by continuity, it's very easy to see. If you know the classes are perfect, then this B infinity is unobstructed. That's just sort of immediate. But then to have a staircase, you need these classes to actually be live at B infinity, not at their center point, not at the BK, which is this approximation. So, because you want to have at B infinity, you want to have infinitely many non-trivial obstructions to have a staircase. And so we need more estimates, of course, and actually this is where Usher's estimate came in useful, because he had exactly the same problem. He had classes which are live not quite at the right point and had to have an estimate to make sure they're live at the right point. Okay, so that's sort of the conditions, you know, that you have to check. You have this special kind of sequence which you have to find and check that it has the right properties. And then you need to check perfectness, which is a pain. You have to check these classes reduce properly under Cremona transformation. And then you need to check these estimates to make sure that they're live at the right place. Okay, now pre-staircases and blocking classes. Yeah, this is what I was thinking. So the point is that the coefficients of the blocking class determine the relations of the associated pre-staircases. So this is something we discovered. We noticed that, you know, all our potential staircases had these relations, and we hadn't a clue what these relations were, except it allowed you to give a nice description, sort of neat description of the staircase. But here we have a theorem. Suppose we have a B, which is a blocking class. So that means that, you know, at this center point, the value of the obstruction here is bigger than volume. So it's blocking at the center. It then blocks some interval IB, and then which is a Z interval, because it's an I interval. And then, you know, it's saying that if the ascending pre-staircase accumulates at the lower endpoint of this interval, then its relation has to be this. So the relation involves D, M, P, and Q from B. So it's 3M minus D times dk is equal to M minus Q M times pk plus M times qk. And similarly, if you have a descending staircase accumulating at the other end, then the relation is determined in a similar way. You always get this coefficient 3m minus d. That happens for all our staircases. That's always a coefficient of dk. And then you get a slightly different relation here. But that means then, you know, that if you know the blocking class and you know its coefficients, then it really gives you a huge clue as to what the associated staircases are, because you only need to know what their steps are, and then you know this relation from the blocking class, and then you have to check all the conditions hold. But you know, it gives you many, many potential staircases. And here is an example where you take, again, the U classes, the relation I said was 2n plus 3, and then times d, and then n plus 1 times p, and minus n plus 4 times q. And the blocking class is D has n plus 3, M is n plus 2, P is 2n plus 6, and Q is 1. And you could just check that this is what you get. Okay, so 3M minus D is 3 times n plus 2 minus D. So that's 2n plus 3, etc. Okay. So to sum up again, we found 3 sets of blocking classes and associated 2 periodic staircases. We've got this family BU, we've got a family BL, and we've got a family of BE. And I don't think the names are ideal, but anyway, those are the names of the families, right? So U stands for upper, L stands for lower, and E is just a different letter. So we have our 3 families. And we conjecture that these are the only 2 periodic staircases with Z and B in these given intervals. So you see the given interval here, the Z interval is from 6 to infinity, and the corresponding B interval is from 511. So if you look at the accumulation of 511s, that's 6. And the accumulation of 1, of course, well, it doesn't really exist, but that's infinity. So this B interval corresponds to that Z interval, and we're saying, well, these are all the 2 periodic staircases there. which may or may not be true. We don't know. We haven't really looked enough. And then the second set, the L1s blocks a B, goes from 0 to a fifth, and the Z intervals are from 6 to 2 to the fourth. And again, well, 2 to the fourth corresponds to 0, and 1/5 corresponds to 6. And then our other interval goes from 1/5 to this number here. It happens to be 19/61, which is the Z value corresponding to 35/6. And this is less than 1/3. So this is our other staircase family. And we really have this in for historical reasons. It was the first one we discovered. So, we first proved things about that, and then we found the other ones. So that's why we have this slightly funny set of classes. So then, we've actually proven all this, that all these staircases satisfy the right conditions, but we've proven it almost case by case, which is not an efficient way when you say, well, really, there are infinitely many of these things. So we're going to write a second paper, which we hope streamlines the proof and sort of proves some of our conjectures. But, the claim is there are more blocking classes and staircases blocking B intervals from 11/31 to 5/11. So that's a little bit less than this B interval. And the Z intervals are from 35/6 to 6. And these staircases are meant to be, you've got this reflection, which is given by this formula here, which has fixed 0.6, you can check, takes infinity to 35/6, and fixes Z. And so all the staircases which live for these B values actually, for these Z values, these are Z values, for these Z values actually reflect the staircases with these Z values. That's the claim. And these transformations like this behave really nicely on continued fractions. So you can see that your staircases reflect, the staircase steps reflect the families of steps, which have all the right kind of properties. And this particular reflection here, it fixes 6. And it fixes this blocking class, BU, because that's centered at 6. And it's meant to interchange its two staircases. So that we haven't completely proven yet, because we've been busy trying to get the Eller proofs correct, but that's what we expect. And then, so then all the other staircases, all the other B staircases will reflect to something there. And then the claim is that, that's just the first symmetry. This reflection symmetry at 6 is the first symmetry. And there are further symmetries of the problem connected to the sequence of numbers, which when you look up the atlas of sequences of numbers is actually called a bisection of the even Pell numbers, or the half a bisection of the Pell numbers. And what it means is you take the Pell numbers, take the ones in even places and then divide them by 2. So that's some of the, it's related very closely related to the Pell numbers, which are the numbers that come up when you look at the you map into the polydisk. You get Pell numbers, and all the symmetries are related to Pell numbers rather than Fibonacci numbers. So let me explain a little bit more about these symmetries. So we've got this sequence here. And this sequence, well, one way of thinking about it, it gives you the values of Y, for which if you try and find an integer to solve this equation, you can. So that's a set of Y's for which this integer equation has a solution. That's one thing you could say about it. The other thing to say about it is that if you look at ratios of successive ones, like 6/1 or 35/6 or 2/4/35, the corresponding VB value is rational. Which of course is related to the fact that you're taking the square root of 1 in the set place in the equation where you solve it. And so you get now this is not the only set of numbers with this property. There are other sets of numbers with the property, but it's the only set where it is sort of the simplest case, where the square root you have to take is the root of 1 instead of the root of 9 or something else. Anyway, so we have this set of rational values. And then the other thing to notice is that this sequence of numbers, it does satisfy a recursion, which is related. This point here is a limit point of a recursion, and it's actually the limit of y plus 1 over yi. So, the ratios 35/6, 2/4/35, that's a sequence of numbers, which is sort of starts at, you know, it starts at infinity. If you take 1 over 0, that's infinity, and then you get 6, and then you get, and these ratios here, and it converges to the special point, the accumulation point of a third. And then if we look at these shifts, so this is sort of doing a recursion. It takes an interval like this, which is an interval between two numbers of this form, 2 places down. So it takes 35 over 6 to infinity to 1189 over 204 to 35 over 6. And we conject that that's a shift, you know, it just shifts, and it actually preserves, it takes the staircases we have here in the upper interval, which live for b bigger than 0, 2 staircases in this interval, which I called I3. I'm not sure. Yeah, this is I3, this one. And it also has the same b value. So that's our symmetry. That is just shifting everything down. And then, of course, you could repeat this infinitely often if you just instead of considering this, you know, this is like y4 over y3, you take y6 over y. So you have further one. So this shift takes I to I plus 2. It moves it down 1. And it takes the blocking classes stairs with z and I to the ones with z and I plus 2. And it goes down by 2, and going down by 2, it preserves whatever b is. If b is bigger than a third, it preserves that. If b is less than a third, it preserves that. And some of that is proven, but not all of it. And then the claim is that these symmetries of this form behave really nicely in terms of continued fractions. So you can, for example, if you look at this symmetry, which looks rather horrible, you think, what on earth are looking at that for? But then if you look at a continued fraction of the form 6k L2 L3, where these could be any integers, and you do it by, this is bigger than 6, by the way, then it goes to 6 plus k times this. So it just has this very nice form. Yeah, this shift, this map here is not one of the ones up here. It's not this one, because this is a slightly different one. So probably it's inverse or something. Anyway, it's probably the inverse of that shift. Anyway, so you can really see what you're doing to the staircase classes, you know, the centers of the staircase classes. But the fact is that the action, you know, our classes don't only have staircase classes, they have DM coordinates, which are the linear coordinates. And the action on the linear coordinates is much more mysterious. And that's what I really want to understand before trying to write down more proofs in general, because otherwise you just have to treat each case separately, and that's a nightmare. But now to compare with Usher was in a situation where he had 2 extra classes here, because he was looking at S2 times S2 blown up many times, where the S2s have different sizes. But the point is that the S2s numerically are the same. They both have self-intersection 0, and C1 is 2. So there's a symmetry between S1 and you know, these 2 spheres. And so he could encode all his he had 4 variables, because he had the size of both his 2 basic classes, but he encoded all his variants in terms of a single Diophantine equation. And he used that single Diophantine equation to do his miraculous Brahmagupta move. Now, we can't do that. I don't see how to do that. I've tried to, and his method doesn't work in this case, that I can see. But that, you know, this is something that I want to figure out what you can do to try and, because we know the action of our symmetries. We know what they have to be on P over Q, and we need to figure out what they do on D over M. And, you know, I can find formulas for it, but I don't have insight. And the difficulty is that when you want to, you know, it's fine for just checking numerical things, but if you want to prove the class is reduced properly, you have to take all the, you know, you have to take DM and the weight expansion of P over Q. And then the DM, when you start reducing it, they all get mixed up in a soup. And so you've really got to understand what's going on with those coordinates. They don't, you know, you can't separate them out. And then the last thing to say is just about the structure of these sets. Block, remember, was a set of B's that were obstructed, and that's obviously open. And stair is a set of B's where you have a staircase, and we don't really know much about that. And the other thing we know is that stair sits inside the complement of block, but is not quite equal to it. And so you see, I've described you 3 families of blocking classes, and then you can take all their images under the symmetries, which I have checked that they do mostly exist, the ones we want. And they all define intervals in block. I also checked that the blocking classes, and they all seem to have associated staircases. Well, that's a seems, it looks likely. But in fact, the staircase classes themselves are blocking classes. That's the point. We have many, many more blocking classes. And therefore, you know, we haven't really investigated this, but you know, these staircase classes, we looked at one of them, which sort of lay in between two B0 and B2, the blocking class B0 and blocking class B1. There's a staircase class which is sort of in the middle there, and it seemed to have 4 periodic staircases associated with it. So that's where we think our 4 periodic staircases are going to come to. And then if you have a blocking class with a 4 periodic staircase and another one with a 2 periodic staircase, then in the middle you'll find a class, you'll find some staircase which has a 6 periodic staircase, something like that. But that is all not proven. So the thing is that block may be dense. We don't know. And we're going to post our paper. The deadline is Monday, so it really should be up soon. And then at some point we will prove more things. But our first paper proves about our first 3 staircases and sort of develops all the methods, shows you how we found the staircases, etc., etc. Okay, so this is time's up. Okay.
Right. Thank you very much, Dusa. So applause goes hard through Zoom, but we try. So any questions? We weren't.
I guess I have a question.
Mm-hmm.
If you wanted to actually construct all these staircases that you find, do you see any possible way to do that by, you know, adapting this Casal's Viana construction, for example?
Well, they never construct staircases. What they do are construct full fillings, which are in the corners of the stairs.
Right, right. But
because some of our staircases are very obstructed, right? I mean, they've got this big obstruction class. You cannot, if you look at the value of B infinity, which is the limiting value, you're not going to be able to find full fillings there. But what you might do, if it's really true that all the staircase classes are perfect blocking classes, then at the end of each staircase class, if you look at the, say you've got 2 staircase classes, one above the other, and for one thing, those blocked intervals are disjoint, and it's unobstructed at the end of each of those intervals. And therefore, you might be able to find a sequence of values of Bn tending to B infinity for which there are full fillings. Right, you won't be able to fully fill B infinity itself, at least
right.
Not that because I never really looked at what they've done. I mean, it may be if you're clever enough, you can do this. But the other thing is you do have the limit, the value, the possibility of changing the value of B you're looking at, because B is not rational anymore. But you might be able to find. You may be able to find, for example, rational B. We may be able to find that there are, for each staircase, there's somehow a sequence of rational values of B which converge to the limiting point and which are unobstructed. And then you might be able to find nice things there.
But Dusa, can you repeat, for which B do you have a staircase that touches the volume constraint? I didn't get that.
Well, every staircase limits on the volume constraint.
Right, but before
which ones do you have it touches the volume constraint?
All the time.
Well, we never looked at it. We never looked at that question. We were just eager to prove that that although there might be big classes that nearly obstruct the staircases, they don't completely obstruct them. But I think those bad classes seem to exist for descent. There's one particular bad class of degree 3 that somehow is sort of a big, nearly obstructive class. And that lives for the staircases, the decreasing staircases. The increasing staircases doesn't seem to matter too much. And it lives for the ones which are where B is in between 1/5 and 1/3. So for the U staircases, the ones where B is large and bigger than 1/3, those ones you might be able to show that they touch but we were more concerned. Our problem was, can we find staircases?
Right.
And we've spent all our time trying to show that, yes, indeed, we can find staircases, what the structure is, but we haven't investigated really carefully whether whether sometimes they really do get to the volume curve or not. But they may or may not. It's not clear, because the thing is, what happens is that it depends what happens. You vary B all the time. You see, each, as I say, each blocking class sort of blocks something. As B changes, the interval that it blocks on the z-axis varies. And so, you will, for it to touch the volume curve, you might have to vary B. So it's not at all clear to me that at B infinity, these classes touch B. I mean, you can look at that. We just haven't. I don't think we've looked at it.
Sorry, Dan.
Oh, can I just make one remark, which is just that, in our paper, we do have some staircases that don't touch the volume curve except in the limit, but nevertheless, we are able to construct the optimal embeddings, even though the optimal embeddings are not going to be full fillings.
Yeah, you're right. They're also, those are the ones which have sort of 3 periodic symmetry, as far as I understand.
Mm-hmm.
They have 3 periodic symmetry, and they're like the staircases, for example, at B = 1/3, which is has a very different structure from these pre-staircases I'm looking at, which always have a sort of 2-fold symmetry.
Mm-hmm. Mm-hmm. Mm-hmm.
And if they were your staircase with a 2-fold symmetry, your sort of almost toric fibrations are based on a triangle, and they do touch the volume curve. I think that's what I was told by Anna Rita and Tara.
Mm-hmm.
So, we don't deal with all the staircases we find have got 2-fold symmetry.
I see.
And you certainly might be able to. Now we understand, we sort of figured out what these staircases are. And, I'd say the U staircases are the easiest ones to look at. We do actually have some pictures of the U staircases, but I haven't, I've been so involved in trying to make sure all our arguments are actually correct to prove the estimates hold, et cetera, that I haven't looked at that question.
Okay, makes sense. Thanks. Felix, I sort of interrupted you. Were you gonna?
Oh, I just remembered from all the staircases I have ever seen in the last month, they really all come from, well, one step comes from the previous one by mutation. And once you have this, things get much more transparent. So I think it would be extremely interesting to see whether it can be done here. And also, if you have a foregone as the almost toric basis, it doesn't matter. You inscribe a big triangle, then you mutate the foregone, and you still get a triangle, which is the same ellipsoid.
Well, look, it'd be great if you looked at it. I haven't looked at it from this point.
In this case, I did not. I just would wonder I would be very surprised if mutations do not clarify things.
Well, they might. I'm not saying they don't.
Symmetries should be visible there. So,
I'm just saying that you can, that might be very interesting. But, one thing is that I will say all our staircases are 2-fold staircases, and the other ones that we think we found are 4-fold, etc. And so they do not have the 3-fold symmetry that the 1/3 staircase does, and these other ones where you're basing your mutations on a quadrilateral. I mean, I understand you can approximate a quadrilateral by a triangle, but the fact is that the reason you don't touch the volume curve is that you're approximating a quadrilateral by a triangle. Of course, you're never accurate, so you're always a little bit away. But that's not what's happening here, because those staircases have 3-fold symmetry, and our ones have 2-fold symmetry. And actually, the staircase at 1/3 doesn't have a linear relation. It's not associated to a blocking class. There's no blocking class there, and there's no linear relation. So, there may be lots of other staircases. All I'm saying is, we've done one investigation. This is what we found. We're making conjectures, wild conjectures, that these are the only things that there are. Well, that may be completely off. We don't know. But, we have found some symmetries which really do seem to exist. And I would, what I want to understand is the next thing I would like to understand is how those symmetries, we understand how they're acting on the z coordinates. I want to see what I can say about how they act on the b coordinates. Now, this is a very numerical approach, and there are all these interesting geometric approaches using almost toric fibrations, which are great. So, it'd be wonderful to see what they say.
Just Tara wrote me that a student of her tried that, what I thought, and she says it's hard. Maybe it's too optimistic.
Well, she was saying I think that she told me that she got stuck after a finite number of times. But,
it's not that the student got stuck, it's that the shape got stuck. So somehow when you're doing the mutation, it's sort of, you're trying to mutate towards an ideal triangle, towards this accumulation point triangle. And what my student found was that at some point you have a part that's horizontal at the top that is stuck during the mutation procedure. And so you can't get any closer to an ideal triangle because the y-axis isn't changing anymore. And so you sort of get stuck away from the accumulation point.
Well, it would be very interesting to explore, what is the what's the analog in what we're doing here of that stuckness? How do you see the stuckness? And if you change B a little bit, perhaps you get unstuck. That's what I would.
Well, and there's
no idea what you're doing, so I don't know.
Dusa was saying something interesting too about, this class, this big class that sort of almost overshadows that dark blue class in her picture, that sort of muddles what's going on in the interior corners. That sort of blocks what you might hope are interior corners. And so it's...
Well, the point about that class, it's a very interesting class, and it's actually the existence of that class that led me to find a relation between the staircases and the blocking classes. But that class, its obstruction always goes through the accumulation point. So it's a sort of sliding class. So, it's a particular class, and because of the structure of our accumulation point, the quadratic of that accumulation point, it turns out that the solution, saying the accumulation point equals the volume, can be given by looking at that quadratic equation, but it can equally be given by saying that this obstruction, which is a linear obstruction, 1 plus c over 3 minus b, that's actually equal to the volume. And so, so that's a class that always sort of slides and always goes through the volume, and it's obstructive precisely on some range of B that I've slightly forgotten. It causes problems for the staircases whose accumulation classes are less than 6, because if the accumulation point is bigger than 6, then the actual obstruction from the class is not given by that formula. But that formula still is a line that goes through the quadratic equation. So it means that all the staircases, the E staircases, and everything else, all the images of those under shifts, the descending ones, are, one hopes, only nearly overshadowed by this class, but one has to prove that, right? It's a sort of delicate estimate. And if you ask your friends who do Mathematica to sort of calculate it, they say, well, it gets impossible to calculate. So you have to actually, but Asher had some nice estimates. You can do something with it, but it does mean doing some work.
Do you have any sense, some of this structure that gets obscured, I forget exactly what word you used, maybe, but where there's a higher obstruction that's blocking it out. Do you think when you stabilize, you would see some of this interesting structure similar?
Well, that class that's doing blocking is not a perfect class, so that's not going to stabilize.
Right, but the stuff underneath it that was...
But all the stuff, the point is perfect classes should stabilize. They should give obstructions that stabilize. So
Right.
These staircases, because they're all given by perfect classes, should stabilize. You absolutely have to check that, but it seems to me that they're given by perfect classes and therefore they ought to stabilize. But and that class, these big sort of slanting classes, and these are not perfect classes. And so they're not going to stabilize. But the staircases should all stabilize.
And I guess you're saying, though, that you might even get more when you sort of stabilize or something. Similarly
well,
to,
I mean, you'll see more because it would be more jagged.
Right.
The accumulation, you know, I haven't really investigated that. So if you remove that class, is that the only obstruction to the thing? You know, and I mean, I sort of developed some techniques that might show that, but in the end, I didn't do that. So one might be able to show, though, there are certainly techniques to try and show that this particular class of degree 3 is the only one that sort of nearly overshadows, and there's nothing else that could cause a problem.
Is there some analog of, you know, like in the ball case, Richard Hind has this folding construction and it clips the top of the stairs. You know, is there some analog that one can do here where there's some folding kind of map and it clips the top of your stairs?
What do you mean by clipping the top of the stairs? I don't understand.
Well, in the ball case, for example, you know, Richard has this folding construction, and the exterior corners of the Fibonacci stairs exactly lie on the folding curve. You know, this folding curve is this 3a over a plus 1 thing, and so when you stabilize, that means you can, you know, you can actually construct the embeddings explicitly for the stabilized problem from this folding curve. And also just the numerology of the folding curve is itself interesting. And so I was wondering if, you know, I guess there's probably an analog of Richard's folding curve for the problem you're studying. And maybe, for example, some of your, if you fix a B, then some of your staircases, you know, some of the corners might touch the analog of Richard's folding curve or something like that.
Oh, yeah. I mean, it's very likely that behavior would persist, right? Yeah, I see what you mean. Yeah.
Right.
I mean, you know, I think there are probably many analogs between this problem and the ball problem, or the square staircase problem. But it's actually, it's quite a lot of work to prove all this. And so there are many other questions that, you know, many things one could look at that we haven't looked at.
Sure.
Yeah, I mean, this paper is about 100 pages long, you realize. I mean, it's not, I mean, it's got various things in it. It's got graphs.
Sure, yeah, I can, well,
you know, it's sort of, you want to get the basic things right before you start asking, at least I do, before you start asking lots and lots and lots of other questions.
Sure.
Doing other things. But I think, you know, I think it's a very interesting example because we found interesting structure here.
Sure.
And, you know, and there are all these good questions you can ask about how it relates to other things.
Sure, yeah, it's great.
All right. So Felix, you seem to have another question, maybe?
Yeah, I just wanted, probably you'll say it, but how did you find the symmetries? So did you try to find, did you write down shift on the continued fractions and back engineer them, or
well, I just noticed that at some point, well, actually, you know, Morgan is our champion staircase finder. So she's found many potential staircases, and you just look at the numerics. And then I suddenly realized that, you know, I got these two staircase families and they're related by this symmetry on the PQ coordinates.
Oh.
I mean, you just look at it. And so then, you know, once you've seen that there is a symmetry there, then you look for other symmetries, and then you look and see, well, you know, what's special about these numbers 0, 1, 6, 35, and so on, and et cetera, et cetera. You just start investigating it. But first of all, we were just completely in the dark, I'll have to say. I mean, for many months we were in the dark. We really didn't find a staircase until last February. And our first effort to try and write this paper said there are no staircases in this manifold, right? Or it didn't quite say that, but it was basically, that's what its title implied. But then we started finding the right place to look, because that's the thing, you know, where do you look? So we did find block classes. You know, those were fairly easy to find. We found, because you can find them numerically, you can find these graphically, you can see that there are these blocking classes. But though we didn't understand the structure and everything, but we could see that some values of B were blocked. And then we started looking at values of B that weren't blocked. And mostly numerically, actually. And then as soon as we, you know, sort of sorted out one of them, then once you've got something sorted out, then you can start working on it in different ways.
All right, so let's see if there are any more questions. Oh, okay. So no, I don't see any other questions at the moment, but all right, we still are gonna stick around a little bit, so we can still ask or so thank you again very much, Dusa, and thank you everyone for this very nice discussion. So